So I'm going to talk about a little bit of advanced variance stuff, just in case you're tired of the kind of Scala marathon this morning and you want to hear some more about maybe Haskell. I've managed to work that into somehow. I hope you'll like how I did that. But now I would just want to clarify, this is not a variance introduction talk. I'm going to show you what you need to know to kind of understand the theoretical ideas I'm trying to work with. But beyond that, this isn't a practical variance application talk. You'll get that this afternoon. I think there's another talk about variance. This one is about a bunch of stuff that I made up. But I think it makes a lot of sense, and I hope it gives you a good idea of just where variance falls short, especially in Scala, where it doesn't work in a lot of cases, and what exactly would be the kind of mental gymnastics required to make it work. So this is where I explain what variance is, and I am not going to spend an hour doing it. So you have three kinds that are supported by Scala. You have invariance, which is represented by when you have something in both covariant and contravariant position, like this, like argument and result type of a function. All of the variances can be characterized as position in a function because everything's functions, right? So we have also covariance, which is characterized by the type argument being in return type position. And contravariance is characterized by the argument being in function argument type position. So the rules that you get for type constructors that are marked with variance or not are characterized by these logical implications in the type system. So for any situation, including invariance, if two types are equal, x and y, we also have that the constructed type is equal. That's always going to hold true. The reverse is not always going to hold true. I'll show you a good example of that later. But this direction of the implication will hold true. So this is invariance. So covariance is the congruence of the subtyping relation. So x is a subtype of y implies that get of x is a subtype of get of y. Get substitutes for any covariant type constructor you like. For contravariance, looks very similar, except the x and y are reversed. Contravariance is the most important kind of variance. All other variances can be simulated with contravariance. Covariance is just double contravariance. And invariance is just double contravariance and also single contravariance at the same time. And you can tell that if you look at the way that things are church encoded in lambda calculus, where any data appears in like a doubly nested argument position. I don't think variance is that important for the practicing programmer, which is weird for someone giving a whole talk about variance to say. But I'm not making the claim that variance is important. I'm making the claim that if you think subtyping is important, then also variance is important. So I don't think subtyping is important, and that's why I don't think variance is important. But if you like subtyping, or if you want to use subtyping, then I think variance is important, and in particular, maybe this is a good counterexample, because one of the outcomes of this is that if subtyping is important, and if variance is important, and if variance is too complicated, then maybe subtyping is too complicated to work with, right? Nevertheless, I'm going to show you just how complicated it is, but we're going to get into that. So here's a more formal reason I think it matters a lot, which is that there's a sort of hole in the typing system if you don't have variance. So here we have type equality, which is the type relation you get in a system without variance. Subtyping, sorry. So you have reflexivity. Every type is equal to itself. It's symmetric. The equality relation is symmetric. There's nothing more to that. It's transitive. If A is equal to B, B is equal to C. Also A is equal to C. Always holds true. Unlike, floating point math equality. And we also have something very similar to the invariant rule for congruence that we showed earlier, which is that two types are equal, also a constructed type is equal applied to those arguments. Always going to hold true. Now, we have similar rules for the first three of those in a simple subtyping system that does not have variance. So every type is conforms to itself, is a subtype of itself. If A is subtype of B, B is oh, sorry, I got this confused. This is actually anti-symmetry, but anti-symmetry is like symmetry, but it has anti in front of it because it's defined a little differently. This just says that when the symmetric relation holds, that means the two types are equal, and that's the only case in which that can happen. If you have either of these not true, then the types can't be the same. And then back to something more simple, the transitive property also holds. A is subtype B, B is subtype of C, means A is subtype of C. Oh, wonderful. But what you're missing in the subtyping implications is something that matches up with congruence. Well, we've already seen something like that, like covariance and contravariance. It lifts a subtyping relation into a type constructor, which fills this slot in. And so we have a more complete system for type conformance. But you need variance to get that completeness. Now there's a more intuitive way to think about the role of variance in a subtyping system as well. So I have a cat, a variable called a cat. It's of type cat. I'm really bad at variable names or names for anything, really. The cat's named Audrey. That's not really important. I just want to demonstrate here that cat is a subtype of animal. So we have cat less than colon animal. Right? I also want to introduce this function, speak. It takes any animal, not just a cat, returns IO unit. I guess maybe that IO is a meow if you pass a cat. It's a woof if you pass a dog. It's give a talk about variance if you pass me. So, even though these types aren't the same, so we have animal for the argument type here, and the type of the cat variable is a cat.type, or cat. Even though those types don't line up, we know that this function call works. And we know that it works because of the conformance relation between cat and animal. So there's this sort of invisible function that's happening right here that gets composed with the speak function. So we start out with a cat, and we need to get to animal. And we can get there by means of the conformance relation. But it is not observable in what direction this happens. So there are two directions this can happen in. One, cat can widen its type to animal. At that point, it lines up, it can be passed into the speak function. There's another possibility though. Speak can widen its type. Now, I mean widen, I'm talking about a contravariant position to argument type, which means that it looks like it's narrowing, but really the function type is widening. And so I'm widening this function type to cat to IO of unit. And now it lines up, I didn't change this type, and I can call the function. There's no way semantically to observe the difference between these two things happening. Even in a system that does not have, a subtyping system that does not have variance. It's not escapable, is the point. Even in a system that doesn't model variance, you still have variance because it's happening anytime you call a function like this. So the only difference is that such subtyping systems have simply failed to explicitly model something that they're doing. There are actually infinitely many possibilities. They're less important, but they more or less break down to these could meet in the middle anywhere. There might be a mammal type somewhere in the middle, and this thing widens to mammal to IO of unit. This thing widens to mammal, and everything works out. So, but it doesn't matter. None of it's observable because variance is there whether you like it or not. So let's focus on Scala. Scala models a surprising number of things pretty well when it comes to variance. One of the things is like a second order variance, which is marking type constructors of kind star to star with their variance. So one of the things about variance is that it looks like you're talking about a property of an argument for your type constructor, but really the variance is about the type constructor that surrounds it. It's not saying something about the A of get of A, it's saying something about what get means. So you can explicitly get at this by writing a function like this. So the interesting thing about same is that it takes any type constructor. Now I've written it like an invariant type constructor, but it could also be a covariant or contravariant type constructor. It will let this compile. And that's fine because this will always work, right? I can always take f of a to f of a. It doesn't matter what the variance of f is. Widening is a little different though. So I've got a, and a is a subtype of b. I can go from f of a to f of b without doing anything. But I can only do that by virtue of the covariance that I've marked for the higher kind f argument. Now widen, I cannot pass any type constructor I want to it. I can only pass covariant type constructors. So this one, invariant is any kind of type constructor, covariant or contravariant or invariant. And this one is only the covariant type constructors. So, well, we're talking about passing arguments and whether arguments can widen and like fit the kind that we've declared for them, which means that we have a subkind relation for variance. So just like variance is talking about subtyping, the notion of variance itself has something like a subtyping relation, which it has to have for a Scala Z to work, because all of our type constructors are declared this way, but we still want you to be able to use it with co- and contravariant type constructors. So it's fortunate that this works. It's really nice that this works. So our kind of top kind of variance, or our top variance, plays the role, if any, is invariance. And then we have these two subkinds, covariance and contravariance. Neither of them is a subkind of the other. They're separate parts. If you start writing like subclasses that change the variance or method overrides that change the variance of a higher kind of type argument, then there's something weird that happens. So here, this you might be familiar with, that seek, the generic seek, is covariant. And it has a mutable version, which extends it, which is invariant. And this makes intuitive sense if you look at the methods within. The mutable version introduces setters which put A in contravariant position. So A can no longer be covariant. But this is fine because Liskov substitution, we restricted over here. This is broader. We can't do the reverse of this. It won't let you do the reverse of this because you said you would keep this invariant, and you didn't preserve that. But when you push that variance down one level, this reverses, which is good because we wouldn't be able to write Scala Z if this wasn't true. And there's a bug, SI 2066, which is about higher order variance, which goes into this in a lot more detail than I really have time for. But what's kind of happening is that because a type argument position is an argument position, every time that you add another argument layer to it, it flips, right? So this order is correct, this order is correct, this order is correct but will not be accepted by the compiler, but I haven't worked out how to derive unsafe coerce from that. Same thing with this one. But this is the order that things should happen in, because you're talking about an argument position. So the variance should be over here, then here, and here, and here. If you've worked with contravariance, then you should recognize this pattern. It's contravariance, except we're talking about variance, so we're talking about variance-contravariance, which means that there should also exist variance-covariance, so we have a generalized system of variance-variance, which is good because we've already demonstrated that there is a subkind of relation between variances, so it's good that we also have variance for that subkind of relation within our type constructors, otherwise we wouldn't be able to write Scala Z. But I think something's missing. And this is one of the things that really bugs me when I try to use variance, which was 1 or 2 times in C#, which is that it's missing a nothing. So it becomes hard to do some very obvious things that you should be able to do with covariance if you don't have a nothing type, a bottom type. And that's what's missing from the diamond. That's what's missing from my little chart of variances earlier. And it's this one, it's phantom. You can tell it's phantom because if you take only covariance and contravariance and take their greatest lower bound, that is only the thing that you can do with covariance and contravariance at the same time, it's phantom. That is, this logical implication right here derives exactly from the logical implications of covariance and contravariance. That is, for all types A and B, a phantom of that A is equal to a phantom of that B. Doesn't matter what relationship A and B have. For this example, you can tell this pretty easily by substitution. All right, so let's say A is string and B is class loader, my favorite two examples. So, all right, so const string doesn't sound equal to const class loader, but if you do the substitution, const string is in, const class loader is in, int's equal to int, so const string must be equal to const class loader. This is incidentally why you can't do the reverse of congruence. You can't strip off an F and expect an equality relation to hold, because this is a counterexample. I've introduced a new symbol, which I hope is eventually adopted in the Scala. It's ghost, spooky ghost, to represent this variance. And I've incorporated it into the complete diamond. So at the top, we still have invariance, represented by any, and then we have first two subkinds, covariance and contravariance. And then below those, I want to emphasize again that this grants you no additional power over simply having both covariance and contravariance at the same time. So it's really the only thing that you could do that's correct. Our nothing variance is phantom, or any variance, represented by our little ghost again. It's like nothing in our subkinding system for variance. So that would complete the system for variance to variance. Unfortunately, it doesn't do quite well enough to do things that you would want to do with monad transformers, for example. There's something big we're missing for monad transformers, and this is where it's going to relate to GHC and Haskell very shortly. When we were dealing with SI 2066, we decided to take off all of the variances for the monad transformers, and this is why. Most of us don't care about subtyping, so we don't want to bother writing our functors with variance annotations, because it's kind of a pain. And if you don't care about subtyping, then you're just wasting your own time. So mostly we want to write our constructors to be invariant, like this. Some people, though, they like to have their type constructors covariant, so they are writing something that's specific enough to satisfy this old option T's F argument right here. Now, this is the only way that you can mark A as covariant. There's sort of an implication here. The variance of A, which is right here in the data, is exactly the variance of F. The problem is that there's no way to represent this specificity. We have to write it this way or this way, and we can't get both. There's no best of both worlds here. If we take off the variance of F, we also have to take off the variance for A. And that's what we decided to do, because ultimately that's more convenient if you don't care about subtyping, like me. But there is a way that you can do this. All right, well, we're thinking about polykinds. We're thinking about variance-like types. So we already have the idea of subvariancing. We have the idea of variance for variance. We have a top and a bottom variance. Well, we have type variables. We have kind variables. If you look at polykinds, why not variance variables? I've introduced the idea of variance variables here with the confused smiley, and I hope this syntax is adopted into Scala forthwith. And so you see our application here. We have confused smiley introduces a variance variable v, and we use v to declare the variance of the type constructor f, and then we also apply that same variance to a. And with this, everything unifies. It will even work in contravariant or phantom situations. If f is contravariant, then option T of that f is also contravariant. This is a similar problem. That is the problem that we had with monad transformers. It's very similar to a problem that GHC exhibits also with monad transformers in GHC 7.8 with the introduction of its type role system. So I include these logical implications because they look a lot like the ones that we've already talked about for the 4 variances. So here we have the nominal role, which is about, and this is the weakest one, just like invariance. It says if 2 types are equal, then you can lift that into any type constructor. That's true. That's basic Haskell, existed before the role system. But roles introduces this new idea of coercibility. Now it's a symmetric relation, so that's why we only have 3 here instead of 4. We have representational role, which is the equivalent to covariance and contravariance at the same time. Its logical implication looks very similar. If A is weakly equal to B, that's sort of coercible, then also that lifts into your F, where F is, its argument is representational. So if A and B are weakly equal, then so are F of A and F of B. And there's a third role, which almost can be used as an inspiration for introducing the bottom of our diamond, which is actually called the phantom role in Haskell. And it has exactly the same logical implication that we have for phantom variance. That is, doesn't matter what A and B are, F of A is weakly equal to F of B, or coercible. I hope that if this is the higher order role problem, much like the higher order variance problem that we have with monad transformers for a Scala set, and it exhibits in exactly the same place, monad transformers. So here, the role that will be inferred for A is nominal. Just like we've defined it just like we've removed the variance from A in Scala's as monad transformer, we have nominal role for this A right here. And that's because we don't know what the role of the argument to M is. So this is so nominal is the only safe choice we can make. But really, what you want is that the role of A depends on the role underlying M. If M's argument is representational, then A should be representational. The same holds true for both phantom and nominal as well. So they have exactly the same problem. I hope that if one language solves this, then that solution is adopted by the other. It's not quite enough to do everything that you want to do. There are a lot harder problems that you could try and solve. I originally included a lot of ideas for solving this sort of problem, but all of them were insane ideas and definitely not worth applying because this is pretty complicated to solve, but it gets even more complicated than this. Because the variance of A here is the result of multiplying the variance of F and G. So if F is covariant and G is contravariant, then A should be contravariant. If they're both covariant, it should be covariant. If they're both contravariant, it should be covariant. If either of them is phantom, then it should be phantom. So what do we have here? Well, we already have the idea of type level functions. And we have this notion that 2 variances map to a variance. So what is that? That's a variance level function, or a variance family, to go along with our variance variables. And that's like a very general solution that's based on kind of expanding the idea of polykines. But I think it's way too complicated. And there are a lot more things here, a lot more complications and a lot more exotic systems that you could introduce to solve problems like compose. But I think that there must be a much simpler solution out there, and I just can't think of it because there are only 4 variances. There are only 4 variances, so there are only so many 2-argument variance families that you can think of. There are probably only so many 2-argument variance families that are useful that you can think of because the rules of variance relationships are always statically checkable just by looking at the various method definitions that you have within a class or a trait. So there must be a simpler solution out there. I'm not sure what it is, but I gave you the design space, so maybe you should go and figure out what it is. That's all my weird ideas here. I've included some resources from which you can rederive some of this or get some better introductory background on these ideas. The top post here is a good introduction to variance. It also includes the diamond, actually. Second one here is the Scala book that I mentioned. Good to look at if you want to twist your mind into tangles thinking about higher order variance. And if you don't know anything about rules, you should probably check that out as well. Otherwise, you can contact me here. That's it. Thank you.
Have you ever tried to draw it from like categorical point of view, like you have covariant factors, contravariant factors, invariant, I don't know, just discrete category, right? What would be at the bottom in your picture?
I don't know. I mostly spend my time only thinking about endofunctors, which sort of gives me like tunnel vision about that kind of thing. But it could be. And there's definitely relationships here that I'm just not seeing, right?
Yeah, I think this is kind of the same line. Maybe we can get different ideas, like using the category.
Well, I hope that you can come up with something. Yeah. All right. Thanks.
Very good.